Hello everybody, and welcome to your first chemical engineering lab. My name is Connor MacFarlane, and I am a senior studying chemical engineering here at the University of Massachusetts Amherst. Today, I'm going to be walking you through an example of one of the most important processes in chemical engineering, separations. The ability to separate a mixture of compounds into their pure components is one of the most commonly used processes in the chemical industry. As the chemical industry has shifted to include more life science-based processes, these separations techniques are now being applied to biological compounds such as proteins. Today, we will be walking through an example of a protein separation that is achieved through ion exchange chromatography. Chromatography is a type of separation that passes a mobile phase, such as a liquid mixture, through an immobile phase and exploits a difference in the properties of the compounds in the mixture. Ion exchange chromatography exploits a difference in the charges of molecules to selectively bond and unbond certain molecules to the chromatography column. The column is shown here by the positively charged ions that make up this wall, and you can see the mixture of charges that are passing through. Due to the basic principles of charge interactions, the positively charged particles are repelled from the positively charged wall and pass through the column, while the negatively charged particles are attracted to the positively charged wall and bond to it. Once the positively charged particles are all the way through the column, a solution known as an elution buffer is pumped through. This solution contains very strong ions that can overpower and replace the negatively charged proteins that are bonded to the column. As you can see in this graphic, another negative ion forces the attached negative ion away, allowing it to elute out of the column. In our experiment today, we will be separating a mixture of two proteins, lysozyme and bovine serum albumin. Now that we understand the theory behind our experiment, it's time to apply what we have learned. All right, now we're down here in lab and we're going to go through what this experiment looks like in reality. So here we've got our different solutions set up. This Erlenmeyer flask contains RO water. This contains our loading buffer. This is our protein solution, and this is our elution buffer. We're going to be using this pump to continuously pump fluid through the top of the column, down through our resin here, and out through the bottom to our UV-Vis spectrophotometer. So the way this works is we run RO water through the column first to help remove any impurities. Next, we take it and we switch this pump into our loading buffer, which we are using a basic solution. And then we turn the pump on, and it flows through this pump, down through this valve, and all the way up into the column itself. So this is going to take a little bit of time for the loading buffer to go all the way through the system, but eventually we will see it exiting the system through this little tube here. And so you can see we're pushing little droplets out, so we know that there is flow through the system. The way that we're going to add our proteins to this system is through the use of a syringe. You can see on the end of the syringe here, we have a filter to make sure that any impurities that we obtained during the development of the proteins does not get passed into the column. So we're going to disrupt the flow of the loading buffer by turning off the pump. And then we're going to manually disconnect at this joint here to be able to connect our syringe. So now that we've disconnected the tubing, we're going to take our syringe and apply it directly into this opening. Now, I'm going to very carefully start applying a pressure and loading the proteins into the column. And so now that we're reaching the end, we want to make sure we get every last little bit of protein out, and then we just disconnect the same way we connected and connect it back to the pump. Voila. Now we're going to turn the pump back on and continue pumping the loading buffer through to help elute all of the positively charged protein, in our case, the lysosome. And so now that we've got our proteins in there and we're continuing to pump loading buffer through, we're going to take a second and look at our UV-Vis spectrophotometer. And so this is the computer that collects all of the data from the spectrophotometer, and it plots it on these curves. And so on the y-axis here, you have absorbance, and on the x, you have wavelength. And so we use these curves to obtain the concentration of the protein that is coming out in the solution. And so now that we've successfully gotten all of our positively charged protein out, it's time to elute our negatively charged protein that's weakly bonded to the resin in the column. To do that, we're going to use what's called a dilution buffer. In our case, we're using a NaCl and water solution, so a salt water solution with a concentration of 1 molarity. So we're going to stop the pump, transfer over to this solution buffer, and simply turn the pump back on. And so now we're pumping the solution buffer through, and the negative charge of the chlorine atom in the salt solution are going to kick out the negatively charged protein and force it down the column and into our UV-Vis spectrophotometer, where we'll be able to get the absorbance and therefore the concentration coming out. Now that we are done collecting data in the lab, it is time to analyze our results. The curve here shows the light absorbance at a given time during the experiment. As you can see, there are 2 distinct peaks. The first represents the positively charged protein, lysozyme, being passed through the column with the loading buffer. The second represents the negatively charged protein, bovine serum albumin, being eluted at the end. We can use the relationship between absorbance and concentration to calculate the amount of each protein that has left the column, and then compare that value to the amount of protein we put into the column to determine our yield. I hope you all enjoyed this overview of a chemical engineering separation, and please feel free to reach out to the UMass Amherst Chemical Engineering Department if you would like to learn more. Thank you for listening.